On behalf of NZGS, I welcome everyone to the first of series of webinars related to the recently updated NZGS modules, starting with Module 1, overview of the guidelines. We have a fantastic panel of experts joining us today, so I hope you're all looking forward to it. The webinar is divided into two parts. First, Professor Misko from University of Canterbury will provide an overview of the Module 1, following by a Q&A session. If you have provided your questions in advance, Misko will address them following his presentation. Any new questions or comments, as Holly has already indicated, please write them on the Q&A option in Zoom. Following the Module 1 Q&A session, Stuart will present a second part of this webinar on designing for uncertainty interim seismic hazard guidelines, which has been developed on behalf of the NZSEE, SESOC, and NZGS advisory group, and that session also be followed by Q&A session. So to start, Professor Misko and Kevin McManus have played a significant role as a lead authors in the update of the Module 1, which provide an overview of the module series and the seismic hazard values for geotechnical design. The recent update includes significant interim changes to the PGA and the earthquake magnitude values for geotechnical design in some areas of New Zealand. So we are very pleased to have Misko today, providing us with the overview and answering any burning questions you may have. So without any delay, I will now pass on to Misko. Thank you.
Thank you, Emilia, and hello, everyone. Welcome to this first webinar in the series. As Emilia pointed out, I'm going to discuss Module 1. We'll provide an overview of Module 1, and we'll really focus on the key hazard updates that are incorporated in Module 1. I will have a couple of parts of the presentation. First, we'll present the overview, and then we'll cover all of the written questions I have received so far. And then it will be followed by a Q&A session that Emilia is going to moderate. So I hope you can see the slides. I will focus on Module 1, which is really having several roles in the context of the guideline series. I first want to acknowledge a large number of people who have contributed to the development of these modules, including a number of organizations and a number of people. And on the editorial committee, you see the top 4 people were the key contributors to Module 1. With Kevin, we've started this a long time ago in 2006, and we have been the 2 principal contributors to Module 1 for the 3 versions that have been published so far. And of course, I'm going to focus on the latest version, which is revision 1, published in 2021, November. So what is covered in Module 1? There is a brief discussion around objectives, scopes, and regulatory context around the building code and guidance. Mike Stannard contributed to that part in particular. Then there is a new section discussing current limit states that are used in design, SLS and ULS in particular, but then the importance to consider other limit states, especially in the context of performance-based design. I think that is a nice addition to Module 1, which provides some wider design perspective for the use of geotechnical parameters in the assessment and design. There is brief description of earthquake geotechnical hazards, and then the focus is really on section 5, which focuses on estimating ground motion parameters that are used in geotechnical assessment and design in particular. 3 methods are identified. Method 1 is really based on generic probabilistic seismic hazard analysis, in which the National Seismic Hazard Model of New Zealand has been used, and values are provided for PGA and earthquake magnitude in particular, with reference to geotechnical design. Method 2 and 3, method 2 is really site-specific probabilistic seismic hazard analysis, so a little bit more detailed assessment of the hazard at a given location. And then method 3 is a site-specific probabilistic seismic hazard analysis, and in addition to that, site response analysis, site-specific site response analysis. There is also at the end a section providing an overview of all modules in the series. And at the end, a table is published in which the PGA values and the earthquake magnitude values are summarized, and these are the values recommended for geotechnical assessment. The two sections highlighted in blue are really the most important that I will cover today, which is method 1, or estimating hazard parameters based on generic probabilistic seismic hazard analysis, and then the summary, which is provided in table A1 of the module. Just a brief discussion on the regulatory context to emphasize that a number of different pathways have been identified for demonstrating compliance with the code. There are prescriptive acceptable solutions and verification methods. And in addition to that, there are alternative solutions, which are considered really appropriate for complex geotechnical systems, recognizing the variety of issues that we deal with in earthquake geotechnical engineering. And we set the tone by generally suggesting that geotechnical guidance, as opposed to rigorous codes and standards, and alternative solutions, as opposed to verification methods, are recognized as the preferred pathways for geotechnical earthquake engineering because of the complexities of the issues, the uniqueness of the site and problems that we encounter. And for that reason, we have to recognize this distinction early on. Just one slide on limit states and the need to consider, in addition to SLS and ULS, which are well established in the assessment and design framework of New Zealand, to consider other limit states, could be intermediate between the two or could be beyond ULS. And we use this diagram to illustrate the importance of such considerations. So on the vertical axis, we have the response or level of damage from low to high. On the horizontal axis is the intensity of the ground motion from low to high. So what we really try to understand in our assessment is how the response and damage are going to evolve as we increase the intensity in the ground motion. Once we understand that, using probabilistic seismic hazard analysis, we can identify the return period associated with that behavior, or what is the likelihood of that occurring on average for the structures that we consider. And this is kind of illustrating the possible deficiencies if you apply this kind of concept to a discrete return periods, such as those corresponding to SLS and ULS. If we strictly follow the code requirements, which are setting the minimum requirements, you can check the performance only for SLS, 25-year return period, and ULS, 500-year return period for most of the importance level structures. And on that basis, you can identify the performance, whether it is satisfactory or not. And there are a couple of cases presented here, case A, or system A, if you like, and system B, which are showing different types of responses, obviously. However, at SLS, the performance is very similar, and also at ULS, the performance is quite similar. So if you consider SLS and ULS in isolation, you might be concluding that actually the performance of these two systems is going to be nearly identical, whereas clearly it is quite different because the onset of damage for case A is much earlier at 40-year return period, as opposed for case B. So if you have two design solutions, one leading to performance A and the other to performance B, even though they nominally both satisfy in similar way SLS and ULS, obviously the performance of system B is going to be much better. And if I am an owner, I would probably invest a little bit more and get performance B instead of performance A. So those are considerations that one would like to consider or incorporate in the assessment in addition to the minimum requirements that the code is specifying. So let's move now to the most important part for today's discussion, which is estimating ground motion parameters for geotechnical design. I'm underlining here because that is really important. We are just trying to address geotechnical design, and that is why we are focusing on a couple of parameters, PGA and earthquake magnitude. This is not to say that other parameters are not important, such as spectral accelerations for the structure that we consider. They're certainly important, but it is not for us to define those. So the focus is exclusively on PGA and associated magnitude, and method 1 in particular, which is using a generic output from probabilistic seismic hazard analysis from the National Seismic Hazard Model of New Zealand. So let me give you a little bit of background on that. As I mentioned with Kevin, we started this somewhere in 2006 or early 2007. And the first module 1, the first version of module 1 was published in 2010. In that period, there was only one hazard interpretation for New Zealand available, and that is the one summarized in NZS 1170.5. In that hazard, actually, the peak ground acceleration is interpreted to weighted magnitude scheme, so PGA 7.5 or peak ground accelerations associated with magnitude 7.5 are presented. Our approach is that we are not going to recalculate hazards, so we would just adopt whatever is available. So simply, we recommended that NZS 1170 hazard to be used in the geotechnical assessment and was referred to in module 1. Then, somewhere around 2014, NZTA Bridge Manual provided new interpretation of the hazard, in which actually the hazard was provided in terms of couples, PGA, peak ground acceleration, and associated earthquake magnitude, which was called effective magnitude. We never understood what is the definition of that one. In principle, this way of presentation of the parameters is beneficial for geotechnical assessment because we would like to use different combinations of PGA and earthquake magnitude to quantify the load rather than use PGA always associated with 7.5. Assuming that these two are compatible largely, not identical, but largely compatible, we suggested that we should move towards the NZTA interpretation of the hazard because it offered better format for the geotechnical design. And that is why in 2016, module 1, which is called revision 0, this is the first time the module is published by MBIE. So we adopted the version from NZTA in the 2016 module 1 version. However, quickly, anecdotically, we became aware that actually, despite the expectations that these two are going to provide similar outputs, actually, for a number of locations, differences were reported by engineers. And in some cases, they reported significant differences between the two, which obviously raised concerns to the editorial panel. So when we were revising module 1 in the period 2019-2021, we decided that we now have to address these hazard differences, despite our principal notion that we should not go into hazard calculations. It was time for us to check what was going on. So these are the issues that were investigated in a specific study, which was supporting the development of module 1, revision 1. First, we compared the NZTA Bridge Manual hazard with the NZS 1170.5 hazards to understand what was going on across New Zealand. Then we performed probabilistic seismic hazard analysis for 24 New Zealand locations. This was done by Brendan Bradley, and he's on the call today. So if you have any specific questions to this, he will be answering those questions. Then we compared the results from the site-specific probabilistic seismic hazard analysis, now site-specific to 24 locations. That output was compared with the hazard presented in the NZTA Bridge Manual and in NZS 1170. We have identified the next locations with significant underestimation of hazard, meaning the site-specific hazard was providing much higher values than NZTA and NZS 1170 were providing. And then we considered some unification. We considered amplification factors, what was happening across different BS30 values or different site classes, if you like, to understand how to better summarize the results from the probabilistic seismic analysis. And eventually, we published the recommended values, which are summarized in table A1 of module 1. So that table A1 really incorporates the outputs from all of these studies. There is a little bit of discussion on all of this in module 1, but there is more in-depth discussion and reasoning provided in a couple of journal publications published in the Bulletin of New Zealand Society for Earthquake Engineering this year in print, and last year were provided online. So let's cover the bullet points that I have shown before in a brief scrutiny. So first, this is a comparison of the hazard at about 120 locations. These are locations that are published in NZS 1170. The only way to rigorously compare the two is to compare them in terms of PGA 7.5, because that is what NZS 1170 provides, and there is no way you can change this to anything else. So we recalculated the bridge manual hazard in terms of PGA 7.5 and plotted the ratio PGA 7.5 for NZTA to PGA 7.5 of NZS 1170 across all 120 locations or so that we compared. The red line shows the ratio for site class D. The black line, pardon, shows the ratio for site class C. And by and large, you can see that there are actually substantial differences. Mostly, the NZTA hazard is 10 to 20% below the NZS 1170 hazard, but in some cases, it is 30 to 40% lower. So they are different. So this is the reason why we decided, okay, we need to perform a site-specific probabilistic seismic hazard analysis to identify which of the two is closer to the current understanding of the seismic hazard. So we have selected 24 locations. These are shown with solid symbols. And as you can see, they're distributed throughout New Zealand. We really wanted to cover all of New Zealand. We wanted to cover different regions of different seismicity. We wanted to cover major city centers of New Zealand. So that is how those were selected. There was a very careful selection process how to identify these 24 locations. And then for each of those, probabilistic seismic hazard analysis was performed at a given location, maybe around the center of those cities or close to it, not necessarily with them. We were not trying to identify the center of each of those locations. And then on this plot here, at the top to the right, there is a ratio of PGA 7.5 from the site-specific analysis, covering these 24 sites, to the peak ground acceleration 7.5 magnitude provided in NZTA, or the bridge manual. And you can see that for 6 locations, the site-specific study provided much higher PGA values on the order from 30 to 100% higher. A couple of those were just slightly above. Then there are a number of locations for which the two hazards are within 10–20% difference, and the probabilistic site-specific assessment is actually giving slightly lower values. And then for a few sites, the site-specific study was providing significantly lower values. So our concern was this one here, that we have identified from the site-specific study 6 locations for which both NZTA in particular, but also NZS 1170 are providing lower hazard parameters than calculated from the site-specific study. An in-depth analysis was then showing, this is now the comparison of the PGA 7.5 NZTA versus site-specific PGA, respective PGA. One-to-one line is showing here. So if the two values are identical, the points should be sitting on top of the line. But we are seeing that for most of the sites, actually, the NZTA bridge manual is providing slightly higher values for the hazard. But then there are these 6 locations for which the site-specific study was providing much higher values. And we found that actually those are sites affected by the Hikurangi subduction zone. So there was new interpretation of that Hikurangi zone and the effects of that zone on the ground motions in the predictions. And that was really elevating the hazard. So you can see those are the 6 locations with red circles around the solid point. And they really follow along the Cubrinovski subduction zone. So we kind of understood why we were seeing certain level of differences. Because the differences were significant, we decided that we have to update the hazard for these 6 locations. Furthermore, we decided that we need to update the hazard also for the adjacent areas. Pick up Wellington, for example. So this is the solid symbol for Wellington. It is green symbol encircled in red. And the other green points here indicate surrounding areas which have similar hazard based on NZTA interpretation and based on NZS 1170 interpretation. In other words, in NZS 1170, all green symbols are having similar hazard. Since we did calculate only for Wellington here, then we adopted the same hazard for the respective areas, as I said, based on both Bridge Manual and NZS 1170. On that basis, you can see now Palmerston North is the symbol in yellow, so the surrounding yellow symbols were given the same hazard based on the calculation, site-specific probabilistic seismic hazard calculation for Palmerston North. So on that basis, we modified a range of locations which are all associated with the 6 locations for which we found significant elevation of the hazard. The next was to address the effects of soil conditions or site class, if you like. The Brendan calculated hazard for 2 VS30 values, 200 and 300 meters per second. We selected those with the reasoning that most of our cities are located on flat land, and representative values for most of the sites were somewhere from 200 to 300 meters per second. So we're not trying to cover everything, but to get some ballpark figure representative VS30 values. So for each of the 24 sites, the hazard was calculated for these 2 VS30 values. And you can see hazard curves here. These are PGA hazard curves, obviously. For Auckland, the blue one is for 300 meters per second. The red one is for 200 meters per second. And then for Gisborne, you can see much higher hazard, much higher PGA values at Gisborne. But again, 2 lines, the blue is for 300 meters per second and the red is for 200 meters per second. There are some interesting observations here. For example, you can see that by the way, this is logarithmic plot. You can see that the red line for Auckland, is always above the blue line, indicating that this softer site with 200 meters per second is going to be showing slightly higher PGA values, which is consistent with amplification that you would expect for moderate levels of excitation. Because notice that PGAs are very low, less than 0.2 G. And in that case, you're getting amplification of soft sites. For Gisborne, you're seeing the same amplification at low PGA, so the red line is above the blue, but then the red one moves beneath the blue once you have significant PGA. So you're approaching 1G. There is obviously very large nonlinearity in the ground, large strains, and you're getting reduction in amplitudes at soft soils. And that is why the red line goes beneath the blue one. So these are just 2 examples for Auckland and Gisborne, showing how the response changes for VS 200 meters per second and VS 300 meters per second. This is a little bit more complex plot. Now, what we are plotting here is on the horizontal axis is the PGA for VS 300 meters per second, and on the vertical axis is the ratio PGA 200 meters per second to PGA 300 meters per second. So ratio of the red to blue line, if you like, is plotted for different levels of intensities. And now what we are seeing here, there are 24 lines with different symbols. So that is the data for all 24 site-specific studies. So this plot is nicely allowing us to plot everything together and to consider what kind of amplification or differences we are seeing between 200 meters per second, maybe representative for softer soil sites, and 300 meters per second, which are representative for stiffer soil sites. And we are seeing what we would expect to see when the peak ground acceleration at the stiff soil is relatively low, 0.1, 0.2 G, we are getting amplification in the softer deposit. for 200 meters per second is going to give you maybe 10% higher accelerations as compared to 300 meters per second. But when we increase the intensity of the ground motion and we go 0.6, 0.8 G, these are now significant accelerations, lots of nonlinearity in the soil is developing. In that case, 200 meters per second, VS30 of 200 meters per second will give you 10% less PGA value as compared to VS30 300 meters per second. But there is very good, well-defined trend. From this, we can derive a conclusion that we are seeing amplification is dependent on the intensity as expected, and it reflects the level of nonlinearity in the ground response. And if you want to use a constant amplification factor, then the one that fits across well is really 1. In other words, if you're not going to account for nonlinearity in the amplification factor, then the best is not to discriminate between the two. You will be slightly reducing the values at a low PGA for class D, if you like, and slightly increasing for high PGA values, but you will be within 10% difference, and that is good enough. What are NZS 1170 and the bridge manual doing in this regard is shown with the red line, NZS 1170, and blue line, NZTABM. Those are the ratios between PGA for site class D and PGA for site class C. We could not justify those relationships based on the data that we were seeing, so we decided, okay, let's go with something simple. So C or D doesn't matter, they will have the same value. What is interesting and important is that since this is now for 300 meters per second and class B is defined in the NZS 1170 as VS30 greater than 360 meters per second, clearly 360 meters per second and 300 are very close. So even class B will be approaching these values. So for that reason, we suggested that the PGA values that have been derived in this study should be applied to all site classes without any amplification or modification factors for site classes. So I'm getting close to the conclusion of this first part of the presentation. Just to emphasize that we developed this as an interim guidance in order to provide immediate information about 6 sites and associated regions for which we identified that the hazard might be substantially higher than anticipated in the 2 codes that we have available at the moment. So we needed to provide that information. We wanted to provide this information to practice immediately. And the second, in addition to that, we acknowledge that at the moment there is an update to the National Seismic Hazard Model, and the new version of the probabilistic seismic hazard, generic probabilistic seismic hazard for New Zealand will be provided in 2023. So that means that this is really filling the gap until that new updated hazard is going to be published. So this is the summary table at the end, in which we have listed all the regions. And now we are providing pairs of peak ground acceleration, MX, and earthquake magnitude for different return periods, covering the whole country in this fashion. So this is maybe for the first time, not maybe, this is for the first time that we have published PGA and associated earthquake magnitudes in module 1, with the idea to maybe improve slightly the presentation in relation to what was offered in the other 2 codes. In the table, you can see there is a bold line for certain titles and certain numbers. Those are the values that were updated. Those are the 6 locations and the associated areas for which we have elevated the hazard, and that is why they are shown in bold. The rest is really a direct output from NZTA with some interpretation for the return periods that we are showing here. After developing the table, we plotted the output. Now this is showing the PGA values across New Zealand for all locations for 25-year return period, or SLS level, if you like. On the left is PGA, on the right-hand side is PGA 7.5. I will use that plot As you can see, for all of the country, PGA 75 for SLS is somewhere up to 0.15 G. So green shows PGA 75 values of less than 0.05, blue is 0.05 to 0.1 G, and yellow is 0.1 to 0.15 G. And you can see some sort of zonation, if you like, for SLS. And we have consistency in the presentation of the hazard in the way we have adopted. This was just to confirm that what we have done is not creating some non-uniformity in the interpretation. The same thing was done for a 500-year return period. Again, if we focus on the right-hand side, now the range is much bigger. So green points are PGA 75 less than 0.2 G, blue is 0.2 to 0.3, yellow is 0.3 to 0.5, and red is greater than 0.5. And again, you can see how different locations move into different regions in terms of PGA 75 values for 500-year return period. Again, we are seeing consistent trends and not much non-uniformity in the presentation of the hazard. So this gave us confidence that what we have done works reasonably well. So in conclusion, method 1 now provides interim PGA and earthquake magnitude values for geotechnical assessment. I emphasize this. This is only interim and strictly for geotechnical assessment. Revision is needed because we have identified significant differences between NZS 1170 and NZTA bridge manual hazards. And it is interim because an updated hazard output is expected in 2023. The approach that we've adopted was to minimize the changes and address only areas with significant underestimation of the hazard, with the principal idea to provide the profession with immediate information about possible elevated hazard in these areas, so that this should be accounted for in geotechnical assessment and design immediately rather than a few years later. Well, that was the first part of my presentation. Yeah, I'm going a little bit slow, I guess. So let me just jump in now to a few of the questions that we have received in a written format. So I've put them in certain order. I received them in an email, so I will go one by one. I will address all that I have got. The first question is, why are the PGAs for Waikato Basin now representative of what would have been the previous PGAs for Class C soil, which it is widely established does not exist? Site-specific seismic hazard analysis studies in the Waikato Basin result in Class D soil and a PGA lower than the previous PGA for Class D. And there is another argument there. This is a loaded question. There are a number of things that we can discuss here, like classification, C, D, that will be addressed in the revision of NZS 1170. But let's focus on what we have obtained here. This is the ratio of the PGAs of soils with different stiffness, different BS30 values. So if you like PGA D to PGA C. And as I mentioned before, there is no clear difference between the two if you have to use a constant factor. One is actually providing the best approximation. So in that sense, until we develop some amplification factors that are going to account for nonlinearity, this assumption and the value of 1 or not discriminating between different site classes seems perfectly reasonable, and there is direct evidence for that. So I would disagree with this comment, which is saying that there is no evidence. Here is the evidence presented for that decision. The second question, table 1A of module 1 specifies two PGA values for Auckland. One is a lower bound ULS value sourced from the NZTA bridge manual. Which values are engineers expected to use for standard residential assessments, via non-NZTA projects areas? So here indeed, from 500-year return period onwards, there are two values. The top, like 0.15 G for PGA and magnitude 5.9 are estimates from the mean hazard. And then the values in brackets are the values provided in the NZTA bridge manual, which is based on consideration of a source of 6.5 at a certain distance, and that is how this 0.19 is calculated. So the question was, which values are engineers expected to use for residential assessment? And this would be my reasoning. I would use the mean hazard value. This is outside the brackets, as that is the principal output from the hazard. However, would check also what is happening when I use the values in brackets. And why is that important? Well, first of all, if you compare the values outside the brackets and inside the brackets, you may notice that here the values in brackets are going to give you larger load. But if you go at 2500-year return period, actually this combination 0.28 G versus 5.9 will give you higher earthquake load. So things are changing as you move across the return period. The second thing to notice is that actually the calculation of the hazard in Auckland region is burdened by significant uncertainties. So you have to acknowledge that there is some uncertainties in the values that we are discussing here. And finally, I just was showing before the need to move away from a 2-point evaluation for SLS or 25-year return period and 500-year return period. You really want to understand the performance of your system across the full range of excitations. So in that sense, the differences are relatively small in view of the significant uncertainties, and we should understand what's happening for both of those. Question 3, is there any guidance on the minimum earthquake return period requirement for a given importance level? And then there is definition to maybe Auckland Council practice, at least that is on the question that I have received. Well, module 1 is not addressing this, but there is a document as NZSEE 1170.0 from 2002 in table 3.2. Annual probability of exceedance is provided, and for in table, sorry, importance levels is first defined in table 3.2, and then annual probability of exceedance is provided in table 3.3. So these two tables in this document cover everything that was asked in this question for all structures with working life between 6 months and 100 years. So the answer to the question is in those documents and those tables in particular. Module 1 has no ambition or scope in defining or redefining those values. Question 4, clarification is needed on how to develop response spectra using method 1 for the 6 locations where PGA or maximum acceleration changed significantly in the interim timeframe before release of the new hazard update. The answer to this is response spectra cannot and should not be developed based on the PGA values that we have reported in module 1. That is explicitly stated on page 24, module 1. Note, the recommendations presented in this module apply only to the maximum acceleration values. They do not imply any modification of spectral values and spectral shape factors presented in NZSEE 1170. Such adjustment of spectra for different site classes is beyond the scope of these guidelines. In the accompanying paper, PGA hazard presented in module 1 cannot be used for that purpose, and scaling of spectral shape factor from NZSEE 1170 using the PGA values recommended here is not appropriate. Well, this is kind of explaining why it is not appropriate. When you develop hazard spectra through polaristic seismic hazard analysis, you do consider the response at different periods. So you're calculating spectral accelerations at different periods, and that is how you then define the spectrum. We have calculated only this point, so we have no idea what's happening there. So there is absolutely no basis for us to say anything else than what's happening with PGA. Question number 5, the Appendix A of the guidelines provide maximum PGA and magnitude. Is there plans to provide any guidance on the disaggregation to understand the distance of the controlling seismic hazard source associated with PGA and magnitude, especially for the 6 locations? And then refers to what we were saying in our paper. We are not going to provide disaggregated hazard as part of module 1, but such options are considered within the update of the National Seismic Hazard Model and the update of the hazard itself, and also are considered within the Seismic Risk Working Group program. I would also point out that in my view, disaggregated hazard provides unique and highly relevant information for design. We definitely want to use it. We just need to find the right role and format for the disaggregated hazard when using generic probabilistic seismic hazard and assessment analysis in the context of design. And this is what this seismic risk working group program is trying to address. So there is sub question to this, suggesting that some form of plots are given in NZSEE 1170. To my knowledge, disaggregated hazard is not considered at all in NZSEE 1170 presentation. The final question, which is a little bit out of scope, is there clear guidance on the factor of safety requirements for slope stability analysis under seismic ULS assessment? I understand engineers are using values anywhere between 1 and 2 for slope stability assessment, depending on static versus ground water summarise. Clearly, this is out of scope for module 1, but I will just give you my opinion on this. Obviously, there are a range of factors. I'll mention 3 important to consider. Well, if you're doing equivalent static analysis, obviously you are severely misrepresenting or approximating the load that we are using in the assessment. Second, this factor of safety cannot be taken outside of the context of the strength of soil and what are the consequences of potential loss of stability. In that sense, having a factor of safety of 1 for different strength characteristics of the soil will imply completely different responses, and one could be acceptable performance, the other could be entirely unacceptable if you're getting flow type of movement or large deformation. And finally, I mean, the meaning of this factor of safety also has to be put in the context of how good is our estimate. One thing is for sure that whatever slip surface we have assumed, it is not going to be the one that is going to fail in the future events. So in that sense, this 1 or 1.1 and 1.2 are proxies in the assessment. So really a coherent interpretation of the earthquake load, strength of the soil, associated displacement and consequences, and what we would like to use in the assessment, rather than stick to a given number as the number that is going to give us the absolute truth. In this sense, there is this paper, it's relatively short read, from Bray and Traversaro. They are discussing a little bit these specific values of the factor of safety. So I think it will be useful if you just check it and see the discussion surrounding those issues. So with that, I will conclude my presentation covering both the overview of module 1 as well as the written questions that I have received. Thank you.
Thank you so much, Misko. This has been a fantastic presentation, and hopefully you cleared a few burning questions already, and really appreciate your input here. So I'm very pleased to see all the engagement with the modules and all the questions that already have been provided. We do have a few more to go through. Also, thank you for Brendan Bradley joining this panel of experts at the short notice. So no pressure here, Brendan. Any questions? I'm sure Misko will pass them to you. First question. What is the actual reason for the difference between the bridge manual and 1170.5? Are they based on different models? And is 1170.5 now significantly out of date? Should we be using these values across the whole of our work?
Okay, this is another loaded question. First, we have to understand that producing seismic hazard output for design purposes is a huge exercise that covers a range of difficult issues that you have to deal with. The recognition of the complexity of the problem is really the first step to start with. And this is an area that has been evolving with time, especially in the last 10, 15, 20 years. There is significant advancement in the probabilistic seismic hazard analysis. Maybe Brendan can jump in later with some clarification in that detail. So we have to acknowledge that. The second is that actually once you get that hazard output, there is possibility for you to modify that output and to adjust it for design. And that has been done more or less for both codes, I would say. For NZS 1170, we may maybe understand more what has been done, not as much for NZTA bridge manual. So I would say there are serious complexities and details and assumptions on the probabilistic seismic hazard analysis on one end, and then in the interpretation, we don't have the details of those things. So in that sense, we cannot explicitly say why they're so different. I would just add that some levels of differences are expected as time passes on. Things are changing, you know, like Hikurangi subduction zone was not a significant subject at all in the previous hazard. Now it is a major player in the hazard. So you're introducing some very important players that may substantially modify the hazard. And from the paper that I was showing, that was one of the reasons that we were seeing significant differences. So, Brandon, do you want to add anything?
Yeah, only just to agree with all those sentiments and then add specifically, in addition to changing inputs in the hazard analysis calculations for 1170 in the bridge manual, which, as you mentioned already, Misko, weren't documented to the point for us to actually understand what were the inputs and therefore what were the differences. There is also differences in the definition of the outputs from those two different pieces of work. So as Misko already described in his slides, the bridge manual provides PGAs, but so-called effective magnitudes. We never really got a formal definition of what effective magnitude was. It's not in the bridge manual. By defining it as effective, it suggests it's not the mean magnitude from disaggregation, which would be what, from a theoretical perspective, would be the most appropriate magnitude to use. So already there's a, let's say, inconsistency there with respect to best practice anyway. The second thing really important would be that NZS 1170.5 is for structures and is not for geotechnical design, and therefore the PGA values that you effectively obtain from 1170.5 are codified in terms of the way that the spectral shape factor gives you a PGA value as a function of the spectral acceleration value at half a second vibration period, which is really what the Z factor represents. So in that regard, the PGA values in 1170 are not related to seismic hazard analysis. They are purely a function of the spectral shape factor, and it just so happens that numerically the PGA and the 0.5 second spectral acceleration value happen to be similar. Sorry, 1.0 second spectral acceleration value happen to be similar. So I think there are differences in the, just to summarize, differences in the calculations which are not documented, so we don't know, and also differences in the definitions of the different versions of PGA and magnitude that have been provided.
Thanks, Brandon. Back to you, Emilia.
Oh, thank you both. So I have two related questions. First, when will the NZ 1170.5 be updated to reflect these changes?
Well, I think you're aware that there is intensive work on the hazard update, and there is also intensive work within the seismic risk working group, and that there is anticipated output in 2023. That is all I can say.
Thank you. And the other one, why only geotechnical? Surely the implications are more broad than this.
Well, as I mentioned in the presentation, we really focus on PGA and associated magnitude. People would know that immediately there are certain methods that we use in which you need the two of those, let's say liquefaction assessment. But PGA is very far from really defining the whole hazard that you need for the assessment. So in that sense, we try to emphasize that point, that we are providing very limited scope in what we are trying to define. And people should be aware of that and should not be extrapolating or scaling other parameters of the hazard based on the PGA. So that is why we are emphasizing that geotechnical angle. Okay.
Yeah, just to add to that, really that was an intended scope limitation to actually make the piece of work manageable. So we clearly recognize that if the PGA changes by a significant amount, then obviously that has some implications for changes in response spectra. But for us to solve that problem as well would have been, several orders of magnitude more work, and hence essentially is the reason why the National Seismic Hazard Model has been revised in a more formal sense to address those broader implications.
Yes, thank you. So another question, will there be an update to the seismic hazard parameters for use in Canterbury earthquake region to reflect the current understanding of the seismic hazard in the region based on the recent studies, and what is the time frame?
Yeah, I mean, obviously, Canterbury is part of New Zealand, so it will be addressed in the update. We were aware of this issue when dealing with Module 1, but we didn't want to create any additional complexity, so we just decided we will wait until decision is made on this particular region. The key issue here is that we are dealing with some elevated seismicity and then predictions on that basis for this region. And it will be best this to be dealt within the probabilistic seismic hazard assessment from the generic output. And at that point, it will be considered. So certainly it will be covered in that consideration.
Thank you. If we have a site that is not located close to any of the sites outlined in Module 1 and Appendix A, should we default to bridge manual, providing it is not close to one of the locations affected by the Haringey zone?
I would say the principles that you would use when using only the bridge manual, that means you're away from a site for which you have specific value, should be applied in this case as well. There is no reason now to change that approach. I would say that if you are really closer to a region for which we have elevated the hazard, it will be appropriate to use those values.
Could you explain if you have done a similar comparison for what is defined as subclass A in 1170?
So sorry, where is that question? I'm trying to identify it.
It's the one from Eleni.
Okay, yeah. So for the class A, okay. No, and there was a question from Merrick as well that I saw. Let me connect it. Where is it?
Yeah, they seems to be jumping around.
Okay. Anyway, let me cover Class B and Class A. So Class B is defined in NZS 1170 in different ways. There are a number of parameters. The strength of rock and BS30 is one of the parameters. And then Class A is really strong rock. Now we have defined here parameters for Class C and D. Let's think, what is NZS 1170 doing, for example, between A and C, or A, B, and C? So you have an amplification factor of what is 1.12, so a 12% increase as you move from one to another for D, and then you have 33% increase when you move from A or B to Class C. We adopted this across the whole spectrum, and essentially that may imply that for a flat rock site, we might be overestimating the PGA values. Flat rock site, okay, rock site, actually they are going to produce very high accelerations. We know it is very, very, very stiff. And the reasoning was also that in most of A and B class sites, you will be having topographic effects, which are in many cases quite significant. And we are not having any intention to quantify those. So if we adopt the value for C in this simplistic approach that we have taken, we are slightly increasing the PGA value for A and B, but that is certainly not above a level that is reasonable to expect for such sites. So in that sense, we think that we consider both A and B indirectly and have values that are good estimates for those.
Thank you. And the Merrick question, which has accidentally been moved to answered. Class B also required the material to be UCS greater than 1 megapascal. The sphericity of the material would be expected to be higher than 360. I would expect Class B material to have a substantial difference to the VS 300 result.
I agree. And I would say everything from 350 above up to 1500 meters per second is within the discussion that I just had. So you may have 10–20% difference from the PGA that we have presented without topographic effects. If we have topographic effects, actually those factors will be very high. So in that sense, for flat rock, maybe we are slightly overestimating PGA, but for most of the sites where you have rock, actually topographic effects should be considered. So in that sense, we are not probably underestimating at all the PGA values. So that is why we thought it would be reasonable to adopt those across board.
Another question, a factor of 50% or 65% are seen that is applied to the ground acceleration of 500-year return period when engineers do slope stability analysis, while this dismisses the real displacement that slope may experience. Can you comment on the ground acceleration needed for slope stability for residual building according to Module 1?
Well, I guess that is related to what I was addressing in the final question. Obviously, we are working with some sort of equivalent coefficients in the assessment for slope stability, and there is significant uncertainty in the whole procedure that we deal with. So I would just suggest that you check different methods and what kind of displacements are going to be as a consequence of a potential loss of stability. And those are the issues that we have to cover. As I said, there is no a certain number that is going to be the right number. Actually, the one thing that we know is that there is impossible to have that kind of static equivalent load that will represent a variety of different dynamic excitations. And that is the uncertainty that we have to acknowledge and deal with, and should be a critical part in the assessment. So that is what I would say. And as I pointed out before, strength considerations of the soil and consequences in terms of movement and types of failure are key considerations in how conservative or unconservative you want to be in the loads and the interpretation.
Thank you. Just scrolling through the comments, what is the recommended guidelines for underground structure?
Well, there is nothing in particular to comment on that. I mean, I'm not sure what is the reference to here.
That's the only...
I'm trying to see the question. Okay. What is the recommended guidance for underground structures? Well, this is very wide open question. In terms of, we are discussing here the ground motion parameters for design. Okay, so there is no any recommendation in terms of modification of those until you have underground structure that goes very deep. And if it goes very deep, then the question is, am I getting some amplification effects at the surface? And to consider that kind of ground response in providing better estimates for the input. But given that we are dealing here with generic probabilistic seismic hazard analysis, what I have described is part of site-specific study and the response evaluation study. In that kind of study, I would check those details, and maybe you may find that the level of earthquake load is going to be lower because you're deep in the deposit. But those are things, as I say, to be addressed in a more site-specific study and detailed assessment.
A very popular question by Stephen: when shall we tell the structure engineer?
When shall we tell the structural engineers? Well, I hope they know this already in some way or the other. Outputs from probabilistic seismic hazard analysis have been around for some time with larger values. So I guess the question is referring to the elevated hazard, but I may not be sure. How do you read this question, Brendan?
Yeah, I think it's exactly in the line that you're mentioning. A simple point I would note is at last year's NZSEE conference in April in Christchurch, there was a session associated with several modules being developed, including the preliminary version of this module 1. And many of you that have attended NZSEE meetings know that a large portion of attendees are structural engineers, so they're certainly aware of these details.
So it's another question.
There are many of the 674 people on the call that I recognize their names as structural engineers as well. So.
Yeah, and look, I believe that many people actually what we are trying to do is to provide up-to-date information, and recognizing that some of that information might be creating not problems but issues that you need to additionally consider, but it is good to consider those now rather than later, and that is why we came up with this information through the interim guidance. A robust update is coming, and that will become soon. In the meantime, we believe what we have provided is really improving that situation.
Thank you. You both. Another question from Ayob. Can you comment on the potential effects of liquefaction and shifting the site period of a VS30 that could modify the PGA values on site response? Are you aware of any research in this space?
Okay, so we have to understand that what we are getting is a result from probabilistic seismic hazard analysis. In that analysis, the ground condition is represented to VS30 is the key parameter that is used, and that covers different types of sites. And at the low end, we would go as low as VS30 is 150 meters per second, which is quite low. And that analysis is going to give you on average how those sites respond and what kind of PGAs, what kind of spectra you're getting across the full range. And we do consider that in the context of probabilistic seismic hazard analysis. And that is perfectly fine to use as initial information and to move on with your assessment and design. If you're encountering issues with liquefaction, then obviously liquefaction studies are going to follow that assessment, and there are simplified or advanced analysis in which you will be exploring those details further on. So I don't see any conflict between the two. They serve different purpose, and we just have to be aware of how to use each of those properly.
Thank you. Another one, by the way of an example, how would these buildings which suffered damage from the Kaikoura earthquake perform under the Module 1 design earthquakes for Wellington?
Very loaded question. And so look, I mean, different buildings with different characteristics exposed to different earthquakes are going to perform in different ways. As we saw actually in the Kaikoura events, many earthquake-prone buildings performed well, and then some relatively new buildings did not perform as well. So in that sense, it really depends on these subtleties of what kind of earthquake load and what are the characteristics of the structure. And that is what we are trying really to do the best we can. So in that sense, a variety of performances would be the response depending on what is going to hit what structure.
Thank you. Just trying to see what else we have not answered. Should we use a maximum from table 1 for attaining structure design? Well, you will use it a maximum, but of course you will have to interpret it. If you're using it in the pseudostatic analysis, obviously that is going to be super large load, and you will have to substantially reduce it, because when PGA is a load that occurs in one very short period of time, it is high frequency response. And what you're using in slope stability or retaining wall analysis is equivalent static force that stays there forever. So those two things are extremely different. If you exceed your capacity for a very short instance of time, that will result in some movement.
a moment of instability, but not more than that. Now, it is really for us to identify whether we are dealing with issues with short instances of instability, which means some movement, whether we are dealing with instances of serious instability and loss of stability with significant consequences and things like that. So in that sense, we just need to provide a robust assessment in which we recognize what the actual loading is and what we are doing in the assessment and how to interpret the two.
Thank you. Misko, there is a quite long question regarding design PGA of Northern area. Rather than me trying to convey, if you could have a look and see if you can answer.
Well, I actually answered, that was maybe question number 1 that I was answering, which was specific to residential areas and whether to use 0.19G with 6.5 or the hazard is saying 0.15G with 5.9. Look, honestly, the two are different, and I understand where you're coming from a pragmatic viewpoint, but they're not dramatically different, I would say as well. And actually, I was pointing out that if you move away further on the return period scale, you will see that the hazard is giving you a higher value than those in brackets. The values in brackets are what-if scenarios. So basically saying, okay, the probabilistic seismic hazard analysis is giving you what are we expecting to see on average in this area. And then the values in brackets are some reasoning by engineers in NZSEE saying, well, we want to prevent and see what is going to happen if we are going to be hit by this particular scenario. So you're having a source of an earthquake close to your site, and what will happen? In my view as an engineer, I would like to know that whether I'm dealing with a bridge or with a residential buildings. That what-if scenario is just going to tell me if I get something like this, what will happen? And you may conclude that, yep, we can accept those consequences, it's fine. Or you may find that actually this doesn't look good. So even though I'm nominally satisfying the ULS criteria and performance, I better do something about that. So in that sense, it is an additional check that we certainly encourage to be done on a regular basis.
Thank you, Misko. We still have a few more questions to go to. One is a clarification. From Ian, did I understood correctly the answer regarding type B rock grant, that the module 1 site parameters for PGA and MV can be directly applied, noting the flood grant and topo influences?
No, I wouldn't go that far. I would just say that what we have provided are values which are not very conservative for flat ground. Now, if you have topographic effects or features, no, those effects can be quite substantial. We are not talking 5% or 10% increase. That increase could be substantial. So if you have a structure of significant importance, clearly you want to check that what-if scenario. When you get more significant topographic amplification, what does that mean? So I would put it in that category for sure. So I'm not suggesting that the way we have done it now, we cover topographic effects, so you can ignore it. So please consider topographic effects in the addition, especially for structures that are sensitive to those effects and of high importance.
So I guess another question related to it is asking how do you suggest we should best capture these effects?
That is a tricky one. It is a tricky one because the effects are nowhere formalized in a. First of all, the effects have significant scatter. You can see anything from a factor of 2, 3, 5 increase in PGA. As I say, you really have to check what it means for your structure. Having in mind that we are talking about, in this case, high frequency type of effects, very short duration. And it really depends on the type of structure you're considering. For some structures, that is not going to be significant effect, even if you increase it. If you increase PGA significantly, the response is not going to increase significantly. In other cases, that might be the case. So it's really having that kind of consideration to bring both the load and the response and consequences in the assessment before we say anything about the significance of those effects.
Yeah, I could just add one comment there, Misko, if nothing else, to give you a break. I think the important thing to keep in mind is that the underlying models that are used in the hazard calculation to then come up with these numbers, although they use a simplified site characterization metric, typically VS30, sometimes the depth to a certain shear wave velocity, for example, 1 kilometer per second, as some indication of sort of sediment depth. That those models are developed based on observational data recorded globally. And so many of these sites will have the phenomena that are being discussed now to various degrees. So some of them may have some topographic effects, others not. Some of them may be soft soils that are sandy, some of them may be soft soils that are clay or silty, etc., etc. So in that regard, you can think of it that the predictive models are giving you sort of like a global average behavior for that level of VS2. And so although there is obviously uncertainty in taking that global average, that uncertainty is represented in the model, and that's why we have probabilistic results that accounts for that uncertainty. So when you make use of those values, there is some uncertainty from a hazard definition perspective that's already included within your calculation. And so really it's for you as the engineer to try and judge to the extent that you can whether you think your site that, for example, has a shear wave velocity of VS30 of 200 meters per second, is it a typical site for 200 meters per second, or is it an extremely abnormal site? In which case then you might want to start thinking about some of those additional considerations. But if it's quite a standard site for 200 meters per second, then actually the models will predict that behavior on average quite well.
Just a couple of comments in relation to these topographic effects and slope stability assessment. I'm reading what Braber wrote down that actually there is some guidance for topographic amplification already. So NZTA Research Report 613. So please check that. And another thing, you know, in the editorial panel for the modules, we've discussed another module on slopes that was always as a possibility, and I think it has been on the agenda, and something might be happening in the future. And as Eleni pointed out, this is something that is seriously considered at NZGS. So I would just refer to those efforts really to support this area, which clearly is of great importance for the profession.
Yeah, I agree, Misko. Thank you for that. And thank you for both of you to answer the question. We will have to move on to the second part of the presentation, but if there's time at the end, we either will continue to answer those questions, or questions will be passed to both presenters to reply to them after the webinar over the next month or so. So without further ado, now is the second part of the webinar. Stuart will present Design for Uncertainty and Interim Seismic Hazard Guidelines that has been developed by NZSEE, SESOC, and NZGS Advisory Group, which will also follow by Q&A session. Stuart is a Technical Director for Earthquake Foundation Engineering at Tonkin Taylor, and he's very passionate about the work he does with the different societies. As before, if you have any questions, please put them into the Q&A session, and I will thus pass on to Stuart, and we move on with the second part of the presentation. Thank you, Stuart.
So, yes, so this guidance is a guidance document which is being prepared by the Joint Technical Society. So the New Zealand Geotechnical Society, NZSEE, and SESOC, with encouragement from MB. So the guidance document talks about uncertainty in the shaking hazard and how we may allow for that in design. The document is about 10 pages long. It's in an initial draft form, and we're hoping to get it out in publication within the next couple of weeks. So uncertainties in shaking hazard. There's certainly considerable uncertainty. There's uncertainty in the intensity of shaking that you could expect for any nominated return period, and that will be quantified in the update of the National Seismic Hazard Model, which we can expect to be released around September of this year. Then there's further uncertainty in how that National Seismic Hazard Model information will be interpreted and applied in our codified hazard. And we'll be hearing more about that in the updates of B1 VM1. There'll be some initial updates, perhaps about November of next year, and then substantial updates in 2025. And as Misko's already said, Module 1 is only an interim guidance, so it too will be subject to change as further information becomes available. But more importantly, and as this guidance document stresses, there is uncertainty in the intensity of shaking that the structures we are designing will feel during the life of that structure. I suppose one thing we can be sure of, it won't be that specific ULS shaking that we've allowed for in the design. It'll be likely something less than that, but possibly something more, possibly something beyond ULS. So in our designs, we need to be thinking about the full range of earthquake shaking. So earthquake shaking, which could be those smaller, more frequent events, we need to be thinking about damage control. And in those larger, rare events, including beyond ULS, we need to be thinking about collapse control. These couple of quotes from the document really give the essence of the document. So if I just read those out. Whilst uncertainty in the ground shaking hazard is out of engineers' control, uncertainty in building performance can be controlled through design. And then design buildings to behave in a predictable, desirable manner in earthquakes, even when subjected to shaking that is more intense than anticipated. So how do we achieve this? So the document is setting out a series of focus areas for seismic design and enlarging on those. So just quickly going through those, it's suggesting that we should be focusing on having regularity in our structures and clear load paths. So I suppose in simple terms, a building that is a cube is going to have less issues than a building which is L-shaped or Z-shaped or something else more complicated in plan. We should be avoiding lack of redundancy. We should be providing robust detailing and promote ductile response and suppressing brittle failures. Should be providing tying between elements, and that includes tying between foundation elements. Need to avoid excessive displacements and making sure that the displacements in the ground are well understood by the structural engineer and allowed for in the structural design. And we need to be allowing for soil structure interaction and ground changes during shaking, so liquefaction effects and the like. So it'll be that last bullet point that I'll be concentrating on in this presentation, but the document does talk through each of those points. So ground can be vulnerable to deformation and reduction in stiffness and strength as a result of earthquake shaking. You know, those sorts of issues associated with slope instability, degradation of shaft capacity of foundations in overload situations, and liquefaction associated consequences of lateral spread. So we need to be thinking about those vulnerabilities as we go through our design and our design objectives. And those design objectives are for a low probability of instability or collapse with ultimate limit state shaking. And that's, you know, we provide that low probability by use of our strength reduction factors. So that's well covered within Module 4. Then a further objective is to be thinking about that we wouldn't expect collapse beyond ULS. Now, that is certainly covered by Module 4, suggesting that we need to be thinking beyond ULS and providing stability. And likewise, this document is really stressing that. What these documents don't do is actually provide specific guidance. This is the document I'm referring to as more general guidance. So later on in this presentation, I'll presents some examples for us to be thinking about how we can allow for beyond ULS design. And keen to get your feedback on that, because as a future guidance document, we'd like to be providing some more specific advice. So what this document is stressing is to avoid over-reliance on triggering analysis. So what it's suggesting is if we have a susceptibility to liquefaction or other vulnerabilities, we should be allowing for that in our design. And what sort of mitigation measures can we undertake to allow for that? Things like considering an alternative site. Now that's going to require early involvement from geotechnical engineers and engineering geologists. And that's certainly what we should be recommending and pushing for. We can undertake ground improvement. We can select forms of foundations to avoid the vulnerability. So piles extending beyond the soil susceptible to liquefaction and founding at greater depth. We can select forms of structure and develop the design of those forms of structure to have more tolerance to the vulnerabilities in the ground. In developing those designs of mitigation measures, it's going to require close collaboration between structural and geotechnical engineers. And probably the most important stage of that is at the concept stage. So I'd like to repeat a quote from a previous webinar, which I'm sure a number of you will remember. The form of the primary structure and the foundation system were jointly selected by the structural and geotechnical engineers in consultation with the architect and the client. So I think it's well worth repeating that, just to once again remind us the way we work together, and particularly at that concept design stage. Then as we move into preliminary design and developed design, it's important that collaboration continues. It's important that the structural engineer clearly understands the ground behavior, and it's important that the geotechnical engineer clearly understands the structural behavior. And further, I think it's really important that we be closing the loop during this design process. So what I'm meaning there is when a geotechnical engineer provides a structural engineer with some design parameters, that there is feedback, that the structural engineer feeds back to the geotechnical engineer what the implications of those parameters were for the design, to give the opportunity for the geotechnical engineer to review or even possibly revise those parameters, to check that the parameters have been applied as intended, and possibly even develop solutions to problems identified in a geotechnical manner. So far through this presentation, we've been talking about avoiding or mitigating liquefaction effect of susceptible soils, regardless of the triggering. But there will be situations where that's just not reasonable. And that could be the situations where the cost of mitigation is prohibitive, and that is in addition, the likelihood of liquefaction and triggering is beyond ULS is very low. So in those situations, there could be good justification for not allowing for the consequences of soil susceptible to liquefaction. Now the question here is whether what we're talking about is a code minimum requirement or a non-mandatory recommendation. So our code minimum requirements are specified in the building code in B1 VM1 and NZS 1170.5. And there's certainly an implication in there that our ULS designs should be providing stability beyond ULS, but no specific requirements. And then as we go through the guidance documents, module 4, as well as this guidance which is about to be published, there's certainly strong recommendations of considering beyond ULS. So probably the answer is that yes, there is some general expectation under code minimum that there is going to be stability beyond ULS, but no specific requirements. But there is guidance there which is being developed. So now I'd like to illustrate some of these ideas that I've been talking about via some examples. And the information, again, I'll be presenting here is more specific in form. So it's not actually included within the guidance documents that I'm referring to, but we would hope that we'll eventually develop this and include it in a future guidance document. So for that reason, keen to hear your feedback on what I'm about to present and allow us to consider that as we develop further guidance. So once again, repeating the approach, what we're trying to design for is ultimate limit state requirements at ULS shaking and having a low probability of collapse under those conditions. Then we want to go on and check for stability beyond ULS. And it is a check, so it's not looking at ULS requirements at a higher level of shaking. So the ULS requirement is a low probability of instability, and we achieve that by using strength reduction factors. So in your stability check, you may well decide to use a strength reduction factor of unity because it's expected behavior that you're interested in rather than a low probability. Now, this sort of approach parallels what is done in base isolation design. So in base isolation design, designers need to think beyond ULS. They need to be thinking about the tolerance to displacement of the base isolators and the width of the rattle space. So the ideas that have been used there in base isolation are similar to what I'm about to present for these geotechnical considerations. So the examples I'd like to talk to is one in Wellington, one in Hamilton, one in Auckland. We're going to assume that all three sites have a similar soil profile, and close to the surface there is soil susceptible to liquefaction. And the trigger for liquefaction for those soils has been assessed to be around 0.3 G. And it's considered that a suitable solution, if we're not concerned about liquefaction, would be shallow foundations for this proposed building. But if liquefaction needs to be considered, then it's to provide stability, it would be considered necessary to pile at substantial additional cost with those piles extending down to greater than 15 meters depth. So for that situation, let's see how we would respond with different levels of intensity of shaking. So first of all, the Wellington site. We've got an ultimate limit state, 500-year return period intensity shaking there of 0.68 G, well above the trigger for liquefaction. So in our ultimate limit state design, we're certainly going to need to allow for liquefaction, which is going to dictate the need for piles. In the Hamilton case, probably not quite so clear cut. At the ULS level of shaking, we wouldn't expect liquefaction. But as we head up to the 1,000-year event, it's possible, and certainly at 2,500-year event, we would expect liquefaction to be triggered. So what we would expect there is for the ULS design, that there wouldn't be a requirement to consider the liquefaction effects, but we would need to then check for stability beyond ULS. And so therefore what we would expect is the project team to be reporting to the client the costs and benefits of going from a shallow foundation solution to a pile solution, and we would expect as a consequence of that the client to select the piled solution. Then the Auckland example, in this case we wouldn't expect liquefaction even right through to the 2,500-year event. So liquefaction affecting the building is considered quite unlikely. So in this instance, the project team once again could report to the client on the cost benefits of shallow foundations versus piles, and provide a recommendation, and the client could well select to go for the shallow foundations. So that brings an end of the presentation, and look forward to hearing your feedback. Thank you.
Thank you, Stuart. That's a fantastic summary of what to expect from the guidelines, and consider that probably quite a few of us, has not yet been aware of what to expect. I'm sure people will have more questions as they get published, and or reflect on it later on and maybe send them later. But one of the questions I have is, considering that these are non-mandatory requirements, what do you do if the client doesn't want to proceed with the recommendation?
Yeah, a common question. I think really as engineers, it's for us to continue to communicate to our clients around what good engineering is, and the consequences of not following that good engineering, and really encourage clients to implement good engineering.
Thank you, Stuart. It would appear that we do not have any further question at this stage. There are a few questions for the module 1, but considering how long this webinar has already been, I would propose that we will take those questions offline and reply separately. And let Misko, you have seen ones that you're very keen to reply as we speak, and
No, I'm happy to answer those questions later on.
Yeah, that would be good.
Yeah.
So yeah, just give people half an hour time to go back and do work, and hopefully reflect on the presentation, and if needed, they can watch it again later on when it gets published. And if there are any questions, please do not hesitate them to send to the NZGS, and we will pass them on to the representative authors and presenters. So Misko and Stuart, on behalf of NZGS, please accept our appreciation for your time in preparing and delivering these webinars. Also, thank you to Brendan for supporting the panel and questions. This has been a fantastic a summary of what has been done by NZGS and the other societies. I'm sure we all get something out of it and had some benefits. And again, if you do have any further questions, please do not hesitate to send them to NZGS, and we will pass them on. Out of interest, Module 2 webinar is planned for October, so please watch the space. That's on geotechnical investigation for earthquake engineering. And we hope if you have any questions, you can again send them in advance to us for, in this case, Rick Vance, who will be presenting for him to answer them. But the format will be very similar to what we have seen today. And I hope you all have enjoyed it and have got something out of it. So thank you so much, everyone, for participating. And again, thank you very much to the presenters.
Thank you, Amelia.